You are tuned to Iri-e-learning, and I am your host, Teacher. In this, our 8th lesson on mole concept, we will learn to deduce the empirical formula of a compound. By the end of this lesson, we should be able to deduce the empirical formula of different compounds given the mass or percentage composition of the elements. Recall from our previous lesson, the empirical formula gives the lowest possible ratio of the atoms of the elements present within a compound. So we start with finding the empirical formula when the mass of the elements are known. Example 1. If a compound contains 1.1 grams of sodium and 0.39 grams of oxygen, what is the empirical formula of the compound? The first step involves recording the symbols of the elements stated in the question. In this question, it is Na for sodium and O for oxygen. Step 2 involves recording the mass in grams for each element, and we record those masses below the symbols. For sodium, it's 1.11 grams, and for oxygen, 0.39 grams. Step 3, we find the number of moles by dividing the given mass of each element by its molar mass. The molar mass is the mass of 1 mole of the element, and we obtain that value from the periodic table, which is the mass number of the element. It's actually the mass of 1 mole. So for sodium, the mass of 1 mole is 23. For oxygen, the mass of 1 mole is 16. Consequently, to find the moles, we will have for sodium 1.11 divided by 23 and for oxygen 0.39 divided by 16. The answers are in moles. Sodium has 0.048 moles and oxygen 0.024 moles. The final step, step 4, is to find the molar ratio of the elements in the compound. Here we examine the values for the number of moles that we found to identify which one is less. After we have identified the one that is the least, in this case it's oxygen, 0.024 moles is less than 0.048 moles, we're going to divide each of these values by the lower number of moles. So sodium becomes 0.048 divided by 0.024 and oxygen 0.024 divided by 0.024. As a result, the ratio is saying for sodium there are 2 sodiums to 1 oxygen. Consequently, the empirical formula of a compound containing sodium and oxygen becomes Na2O because there are 2 sodiums to 1 oxygen. Example 2. A compound contains 0.78 grams of calcium, 0.234 grams of carbon, and 0.936 grams of oxygen. Find the empirical formula of this compound. Following the same steps, first step, record the symbols of the elements stated in the question, and in this question we have Ca for calcium, C for carbon, and O for oxygen. Step 2, we are going to record the mass in grams for each element below its symbol. For calcium, 0.78 grams, carbon 0.234 grams, and oxygen 0.936 grams. Step 3, we're going to find the moles, and we find the moles by dividing the mass by the molar mass of the element. In the case of calcium, that becomes 0.78 grams divided by the molar mass of 40. For carbon, 0.234 divided by 12, and oxygen 0.936 divided by 16. Next, we find the answer in moles for each of the divisions. For calcium, we get 0.0195 moles. For carbon, 0.0195 moles. And for oxygen, 0.0585 moles. Then we find which is the lowest number of moles for the 3 moles calculated. And as we can see, both calcium and carbon have the lowest number of moles of 0.0195. Therefore, we're going to find a molar ratio by dividing each number of moles by the lowest number of moles. Here we go, 0.0195 divided by the same value is 1. And for carbon, it is the same, 0.0195 divided by 0.0195, which also gives 1. And for oxygen, 0.0585 divided by 0.0195, which gives a value of 3. So as a result, what we have is there's one calcium, which we represent as Ca, one carbon represented as C, and 3 oxygens represented as O3. So the empirical formula of the compound for example 2 is CaCO3. Next, we transition into finding the empirical formula when the percentage composition is given. And in this scenario, we consider the percentage composition as the mass in 100 grams. Here is our first example using percentage composition. What is the empirical formula of glucose, which contains 40% carbon, 7% hydrogen, and 53% oxygen by mass? Before we begin our calculations, we should ensure that the total percentage of all the elements equal 100%. So here we have 40 plus 7 is 47% plus 53% gives us 100%. Once our total mass is 100%, then we are okay to continue with our calculations. As we did before, we record our symbols for the elements involved, C for carbon, H for hydrogen, O for oxygen. Then we record the mass in 100 grams. Carbon 40, hydrogen 7, oxygen 53. The next step is to find the number of moles, and we divide the mass by its molar mass. So for carbon, 40 divided by 12, hydrogen 7 divided by 1, and oxygen 53 divided by 16. Our answers in moles become 3.333 moles for carbon, hydrogen 7 moles, oxygen 3.3125. And from here, we're going to find the molar ratio. And as we have always done, we divide through by the smallest number of moles. Looking at our values here, the moles for oxygen is the smallest of the 3 values. So we're going to divide through by 3.3125 for each number of moles. Therefore, carbon becomes 0.333 divided by 3.3125, which is 1. Hydrogen, 7 divided by 3.3125, giving 2. And oxygen becomes 3.3125 divided by 3.3125, which is 1. So the lowest possible ratio for the elements in glucose is 1 carbon, written as C, 2 hydrogens, written as H2, and 1 oxygen, written as O. Consequently, the empirical formula for glucose is CH2O. Example 2. Find the empirical formula for a compound that consists of 36% aluminium and 64% sulfur by mass. Once again, ensure that the percentage composition by mass equals 100% before we proceed with our calculations. In this case, 36% plus 64% is 100%. Therefore, we are good to proceed with our calculations. Step 1, we record the symbols of the elements stated in the question. For this question, it's Al for aluminium, S for sulfur. Then we record the mass in 100 grams for each element. Aluminium was 36 grams and sulfur 64 grams. So remember, we have converted the percentages to mass in 100 grams. Next, we find the number of moles by dividing the masses by the molar mass or the mass number of each element. Aluminium becomes 36 divided by 27 and sulfur 64 divided by 32. So the answers in moles become 1.333333 and so on for aluminium. That's a recurring decimal. And for sulfur, it is 2. Of the 2 moles that we have just calculated, the moles for aluminium is less than that of sulfur. So to find a molar ratio, we're going to divide through by 1.33333. Consequently, the ratio is 1 for aluminium and 1.5 for sulfur, which is an exact decimal, and 1.5 as a fraction is 3/2. However, the molar ratio must be a whole number and not a fraction. So the denominator of the fraction can be removed by a simple method of multiplying the fraction by the value of its denominator. And in this case, the denominator is 2, so we would multiply by 2. However, what is done to one ratio value must be done to the other ratio values as well. So each ratio value will be multiplied by 2. So aluminium becomes 1 times 2, which equals 2. And sulfur, 3/2 times 2. The 2's cancel each other, leaving us with 3. The molar ratio becomes 2 aluminium atoms to 3 sulfur atoms. Therefore, the empirical formula for a compound containing aluminium and sulfur becomes Al2S3. We're at the end of the lesson. Remember to like, share, and subscribe.